Okay, today we're going to talk about parametrics again, and in the last video we talked about how to use parametric equations to model the path of an object, but we focused primarily on an object moving either horizontally along a line or vertically up and down. What we didn't do was focus on how to model the path of an object if it is thrown at an angle, like say you're hitting a golf ball or you're shooting a basketball or you are throwing a football, something like that where the object is launched at an angle. And so that's what we are going to focus on in this particular video. And so let's just talk a little bit about how these equations are to be used. The x represents the x position. So this represents the x position of the object at any time. And this is the initial velocity. So this is your initial velocity that you used. And theta is the angle that you threw or kicked or shot the basketball at. And t, of course, is the time. And y looks similar, except it has two other portions to it. Gravity. So we'll talk about that just like we did in the last video. Gravity will affect the height of the ball and also the initial height of the object as well. And so these are the formulas that we're going to be using. And so we want to take a look at this first example here. And it says, if we could erase this other one. So it says Kevin hits a baseball at 3 feet above the ground. So our initial height is going to be 3. And it says initial speed, so that's our initial velocity. And that's going to be 150 feet per second. And it says it hits it with an angle of 18 degrees, so our theta is 18 degrees. And so essentially we have something that looks like this. An object, a baseball, is being hit at an angle. And the question we want to ask is, will the ball clear a 20-foot wall that is 400 feet away? And so for this, we need to use our calculator and see if we can simulate the path of this object. So we're here with our calculator, and the first thing we want to do if we want to simulate this ball hitting this bat, or should I say the bat hitting the ball over the fence, is we need to change our calculator into radian mode. So we're going to hit menu and we're going to go to our graph and we're going to go to parametric, excuse me, not radian, but parametric mode. And we are going to type in our equations that we came up with. So that's going to be 150 cosine of 18 degrees. And that's going to be times t. And then our y is going to be negative 16 t squared plus 150 sine of 18 degrees times t, and then plus our initial height. And our time, we just have to pay attention to this. We have to ask ourselves the question, how long does it take for a ball to hit a bat and go over a fence? So we may say 5 seconds. I don't think it takes that long, but we could just say 6 seconds or so. It's not going to hurt anything as long as it's not too short. And we hit enter, and we get a certain portion of the ball's path on our screen. Now, I do want to caution you something here. If you are using a TI Inspire, you need to make sure that when you go to your menu from the graphing screen, this is very important, not from the calculator screen, but from the graphing screen, and you need to go to the settings, and you need to make sure that your graphing angle for this particular problem is in degrees. For the next problem we're going to do, it's going to have to be in radians. But you see that the angle that the ball is hit here is in degrees, so therefore we need to graph this function in degrees. So mine is in degrees. You hit make default just to make sure, and there we have it. So we also need to simulate a fence. Okay, so first thing we're going to do is we're going to change our window, and we're going to say, well, we're going to go from 0 to, let's just say 500, because the fence is 400 feet away from the ball. And we'll start for our height. I'll go from 0 to, let's just take a guess. I'm saying the ball may go 100 meters or feet in the air. We don't know, so you just have to take a guess on the y. And there you have it. Now, what we can't see is whether the ball crossed over the fence or not. And for this, we need to make another equation that represents the fence. So we're going to go to Control G, actually. We're going to go to Control G, and let me do that. Control G. And we are now going to simulate the fence. Now, the X represents how far away the fence is. Well, that's going to be 400. And then the Y, this is where it gets a little bit tricky. We need to simulate something that is 20 feet high and basically just a vertical line that's 20 feet high. So one of the ways we can do this, there are some other ways. One of the ways that we can do this is by simply simulating something that is falling down from an initial height of 20. And if you remember the free fall equation, it is negative 16t squared plus the initial velocity plus the initial height. Well, if we just want to simulate something that is dropping down from a height of 20 feet, we don't need an initial velocity because we're not throwing it up first, we're just dropping it down. And we want this fence to be 20 feet high, and so we hit enter, and there in red is our fence. So clearly we can see that for 18 degrees, it does not cross over the fence. And so the question now becomes, at what angle will it cross over? And so for this, we just need to change our angle to 19, 20, and 21, and 22 until it actually crosses over. So I'll hit Control G. We'll go back up to our equation, and maybe we'll skip 19, we'll go to 20, and then we'll go over here to 20. And we see that I'm not sure if it crossed. Looks like it doesn't cross just yet. No problem. So we'll go back in here. We'll do Control G, and we'll go back up here, and we'll just change this angle to 21. So the ball is now being hit at a 21 degree angle, and look like it clears the wall. And so that your answer for this problem would be 21 degrees. Now, let's just say, for sake of argument, that the problem asked us to figure out by how much did the ball cross the fence by. So if this fence is 20 feet high, and let's say the ball went 24 feet high when it crossed this fence, it would have crossed by 4 feet. So we need to figure out by how many feet did this ball cross the fence. So as I said, let's suppose that we wanted to figure out how high the ball was, or by how many feet it crossed over the fence. Well, the algebraic way of doing it, and this is the way I prefer, is to use these equations. And we know, let's just think about what we know. We know that when the ball crosses over the fence, the moment when the ball is over the fence, the x coordinate is 400. So we can put 400 right here for the x. We know that the initial velocity was 150. And the angle that the ball was hit at was 21 degrees. At least that was the angle that got us over the fence. And all of that is times time. Well, we can divide 400 by 150 cosine of 21 because that's just a constant. And we get the exact time when the ball was 400 feet away horizontally. And that is going to be 2.856 seconds. And then what we want to do, we want to figure out how high the ball is at that time. So we're going to take that time and plug it into our y equation, and that will give us the exact height that the ball was at the time when the ball was 400 feet away from where the ball started. So we will say y equals negative 16, 2.856 squared plus 150 sine of 21 degrees, and all of that times 2.856 plus an initial height of 3. When we do that, we get a y height of 26.0025. That's how high the ball is. And then we want to subtract 20 from that because the wall is 20 feet high. So we see that the ball crossed by 6.0025, so approximately by 6 feet the ball crossed over the fence. In this next example, we want to simulate a Ferris wheel, and it says that Jane is riding on a Ferris wheel with a radius of 30 feet. And so maybe we'll say that this distance from the center of the Ferris wheel to the circle, that is going to be 30 feet. And as we view it on the figure below, the wheel is turning counterclockwise at a rate of 1 revolution every 10 seconds. So that right there is the period. They just gave us the period. If you can remember from a long time ago, that the period is the length of time that it takes for an object to complete its cycle. So the period is 10 seconds. We're going to need that in just a moment. And assume that the lowest point of the Ferris wheel is 10 feet above the ground. So we will say that this distance between the Ferris wheel's lowest point and the ground is going to be 10 feet. So we need to come up with parametric equations that we can use in order to simulate the Ferris wheel. So first of all, we recognize that this Ferris wheel is a circle. And we learned in the last video how to write a set of parametric equations for a circle. So the x is going to be the x coordinate of the center. So let's talk about what the center would be. Well, if the radius is 30 and there's another additional 10 feet off of the ground, then that means that the center is going to be 0, 40. See if I can write that a little bit better. 0, 40. All right, so the x coordinate of the center is 0 plus the radius, which is 30, cosine of t. And we'll put that in parentheses. And then y is going to be the y coordinate of the center, which is 40, plus the radius of the circle, which is 30, times sine of t. Now, we have to also take into consideration that the period is 10 seconds. So what we need to do is we need to remember the formula for the period. And the period formula is 2 pi over b. And that is from chapter 4. 2 pi over b is the formula for the period, equals 10. And so if you cross multiply, you will get b is equal to pi over 5. So we recognize this to be a radian value. So that means our calculator needs to be in radians. So we're going to go back and we are going to rewrite these equations in, we are going to use our, actually let's go ahead and put the 2 pi over b right here. So if we rewrite these equations, they will look like x is equal to 30 cosine of pi over 5t, and y is equal to 40 plus 30 sine of pi over 5t. Now I want you to notice something here. In these problems, the angle pi over 5 is with the t, and the other problem that we did, the angle was, the t was outside the parentheses. So please make sure you pay attention to that. And so it says, find Jane's position 22 seconds into the ride. So all we'll do now is going to plug our 22 seconds into our formula. And so x is going to equal 30 cosine. We must make sure that we are in radians in our calculator. Pi over 5 times 22. And then our y is simply going to be 40 plus 30 sine of pi over 5 times 22. And let's see what the calculator gives us. We end up getting, for a position, see if I can find some space over here, the x is going to end up giving us 9.27, and the y is going to give us 68.53. And so that is Jane's position 22 seconds into the ride. Now keep in mind that we could have also used t equals 2 or t equals 12, because this makes a complete cycle every 10 seconds. So Jane's position at 22 will be the same as her position at 12 seconds, which will be the same as her position at 2 seconds.